This is Unit 2 exponential functions, and this is day 3 graphing for exponential functions. Now, what is an exponential function, first of all, and why do we use it? Exponential functions are used to represent changes in population. That's because we typically describe changes in populations with percent. That population is gaining a certain percentage per time period or losing a percentage. Now, populations could be a lot of different things. So when I say population, things that might come up to mind. Species, like a human population, an animal population, maybe a bacterial population. You can also have population be money. The math that we're going to be using in this unit describes our banking industry, our financial systems. It describes how accounts value changes. Maybe the population that's changing is radioactive material. Radioactive decay is how we can actually date how old items are. And there's all sorts of other things that I just can't make a list that encapsulate everything. Those are the three major things that you'll be seeing time and again in this unit and throughout this course. All right, so y equals a times b to the x. That is our standard way to see an exponential function written. A is going to be a constant. It's a scalar multiplier. That's similar to the a that you saw in your function transformations. That a vertically stretched it or vertically compressed it, and that's what's going to be happening here. B is our growth or decay factor. So what happens is A is going to always be the initial population at x equals 0. That can change occasionally according to how it's set up, but let's assume that that's going to be the case most of the time. B is known as our growth or decay factor. So like whenever you're like gaining 20% on your population, B would be 1.2 because you're gaining 20%. You're at 120% of what you were, so you'd use 1.2. If ever you were losing 20%, you'd be at 0.8. All right, so you got to keep this in mind whenever we're going through these problems. Your percent increase and your percent decrease, talking about those, really is found by how far is the value from 1. Okay, if it's above 1, you'll take away 1 from B. If it's below 1, you'll do 1 minus B. But it's how far is this value from 1. All right, this is the parent graph. And what you're going to see here is a couple of unknown values, first of all. You can see that for the parent function, the a value here is 1 times b to the x. So 0, 1 is our initial point here. And then it goes up and it arcs accelerated rate. It's an exponential function. It's for exponential growth. You can see a few things that there is an asymptote here. The x-axis is an asymptote. No matter how far to the left you go here, the graph actually never gets to the x-axis. They run not parallel to each other. The graph constantly gets closer and closer and closer to the x-axis. It never gets there. You can see that on a table of values. I'm going to talk more about that in person if you're in my class. But let's go ahead and actually get one graphed out. So, taking a look at y equals 4 to the x power. First of all, things that I usually do. If there's not an a value written, I go ahead and write one in. I like to see what my a value is. That's going to be a 1 in this case because there wasn't one written. That is going to be your y-intercept because if x is 0, 4 to the 0 power would be 1, and 1 times 1 would be 1. So I can go ahead and graph that point out, 0, 1. Now I can go through and make a table of values, and you can use your calculator for this. That's completely fine. And see what other values you get. So for like x equals 1, plug in 1. 4 to the 1 is 4. 1 times 4 is 4. So 1, 4 is another coordinate. And if I use a 2, 4 to the second will be 16. I'm going to be up off my graph, but I'm going to make mention of it there. Let's go into the negatives. So with the negatives, if I go to negative 1, 4 to the negative 1, talking about that really quick. Remember, with the negative exponent, you reciprocate. So it's 1 over 4 to the first power. It's 1/4. Now, if you keep going into the negatives, you're going to keep getting smaller and smaller numbers. You will never actually get 0. So, like if I go to negative 2, 4 to the negative 2 power would be 1 over 4 squared, which is 1/16. Now it gets substantially closer and closer and closer to 0, but it actually never gets there. You're never actually going to hit this x-axis. It'll never give you a true 0 going out through there. Now I'm actually ready to graph. Now, ready to state domain and range. As for the domain, it is going to be all real numbers. And the reason why, it looks like it kind of stops going to the right here, but it does continue to go. I could do 4 to the 10th power. I get an outrageously absurd big number, but I can do 4 to the 10th power. I can do 4 to the infinity power. It would be positive infinity. I can do all those. I can also keep going to the left here. So my domain is all real numbers. Now, as far as my range goes, it's not. There are y values where this thing does not exist. For instance, it's none of the negative values, nor is it 0. But just after 0, way out here at negative infinity, it would exist. So I'm going to say for my range, y such that y has to be greater than 0. Important to mention, it's not equal to 0. It's greater than 0. All right? So that completes this problem. Now, I handed you out a sheet that listed all the transformations for any function you see. Those transformations apply here. When you have an a value in the front, that's going to be your how much it's compressed or expanded, I said. All right? And also, if the a value is ever negative, it'll be going downward. Now, the h is your left or right movement, and your k is your up or down movement. It is exactly the same thing. The only thing they didn't do is draw in parentheses around the x minus h, but they don't need to since it's up in the exponent. There's automatically parentheses there. Now, applying the idea of transformations, I'm now asking you to graph y equals 4 to the x minus 2 plus 3. Now, the a value did not change from example 1, but because the parent graph is the same, 4 to the x, I'm actually going to use the example from example 1, just transform it. So this is not my answer for example 2. I'm just going to use these points that I had. So, using these points, I had negative 2, 1/16. According to my new problem, I'm going to go to the right 2 units and up 3. So I can take each of these and pick them up and go right 2, up 3. So I'm going to have 0, 3, and 1/16, just above the 3. Going right 2, up 3 for every one of them because that was the h and the k value. So negative 1, 1/8 will be at positive 1, 3 and 1/8. 0, 1 would now be at 2, 4. There we go. I also had 1, 4. So I'm going to go to the right 2 units, up 3. And there I am at 3, 7. So I've actually got a new graph here. Again, transforming my example 1. There we go. This is actually my correct graph. Now I'm going to point out a couple things here. One thing is where my asymptote now is. My asymptote is no longer the x-axis. It is the line y equals 3. So I'm going to actually kind of draw that in with a dashed line there. I always like to see that. Y equals 3. I know that from what the k value is. It's always going to be this k value right here. Really quick, going to mention domain and range, even though it wasn't part of the problem. My domain would still be all real numbers, as is the case with any of these exponential functions, except for cases where they might have trimmed down the domain and range. You will see those in word problems sometimes. My range is now not greater than 0. It is now greater than 3. It will never get to a value of 3 because that asymptote got moved up due to the vertical shift of the graph. I'm going to go ahead and graph this problem, but I'm just going to do it in my calculator. Negative 4 times 1/2. And when I close the parentheses, I'm going to raise it to the x minus 1. Those parentheses are actually really important because that means that the x minus 1 exponent is raising both the 1 and the 2. Without the parentheses, it would only be raising the 2, so it's really important. Now, if you're using this newer software, you'll have to hit over to the right to get out of that exponent before you hit the +2. Please be mindful of that you have to the right to get out of the exponent before you hit the +2. Now I can go to my table, and I'd actually be able to graph from my points here. I'm going to go to my graph, though, and see that this function's actually going down. All right. And it's also a decay function because my b value is less than 1. We're evidently losing 50%. Now, going into what the domain and range is, which is really what the crux of this problem that I wanted to do here. The domain, again, always going to be all real numbers when you're dealing with these problems. My range, not so much. Now, first of all, my range on this one is going to be less than because the a value was negative. I reflected in the x-axis. You need to be mindful of such things. Now, where's the asymptote, not asymptote, the asymptote on this graph going to be? It's actually going to be up 2 units from the x-axis, and I know that from the +2, that is my k value. So y is less than 2. Kind of a strange range to see. Usually, we have positive a values on our functions that we'll deal with in this course. Okay, now on this last problem, I'm going to show you how to set it up, then I'll leave the graphing to you on your graphing calculator and be done. This is the last problem we're going over. And it gives you a lot of information. 1.02 billion people worldwide using the internet in 2006. At that time, it was growing by 19.5% annually. It is not actually maintaining that. We'll get into this in just a second. It says draw a graph from 2006 to 2016. Assume that Y represents the users in billions and X is the year since 2006. Now, that's really important stuff as far as what your variables actually are. So, Y is the users in billion. First of all, it tells me that my initial, I'm going to write a times b to the x, that my initial amount is, I'm not going to write it as this, I'm going to use 1.02 because it did say users in billions. All right, times my growth factor. Now, I know it's a growth factor because they told me it was growing. Since it's a growth factor, I'm not going, 1 would be 100%. I'm actually going to add 0.195 because it's growing by 19.5%. So I'm going to kick that in there. This is now my growth factor, 1.195. Raised to the x power. Now, if ever the population is decaying, it's getting smaller over time, you'll actually subtract it away from 1 instead. But here, you're going to add it to 1. Your growth factor will never be 1. And that's important to know because if it's ever 1, you're not changing as a population. It's just staying stagnant. All right, now that we've got this there, I'm actually going to graph it in my calculator as it is and talk about it. All right, you can see I've actually put that function I came up with in my calculator. When I go to my, if I'm going to graph it, when I go to my window, I'd maybe go use x values from -2 to 12. The reason for that is because since it said from 2006 to 2016, you got to remember that 2006 is actually 0, and 2016 would be 10. So from 0 to 10, well, I went a little bit on either side. As far as my y minimum and y maximum, I went a couple below 0 because I'm guessing people are still going to be using the internet. It's going to go up, obviously. I put in 10 because 10 billion, I don't see it getting there because, you know, there's not that many people in the world. Anyways, when I hit the graph, I got my form right here. This would be a good graph to use, so I used a different scale factor, but that's all right. When I look at the table, I see a couple of interesting things happening. So we were talking about predicting for 2016, that'd be, it would be 6.06 billion people using the internet, and highly doubtful that that was actually achieved. That would be meaning that only 1 out of 7 people in the world would not have the internet. That's just not reasonable. So sometimes these functions don't really work out too well. And the reason is because how much the population is changing by changes. It's highly unlikely that the 19.5% back in 2006 continued. Okay? That would be an insane amount of growth. Now, sometimes that is true, but this wasn't exactly a beautiful problem, you know. So this one, I would say that that's a little bit unachievable. Also, eventually, we would run out of people to get the internet because the 19.5% would be faster than than our population is growing out on the planet. We're starting to level out, we think. So sometimes that comes into effect. End of the day, exponential functions really useful, but they have their limits. You need to have, the more data you have in making them, the better off your projections will be. All right, that wraps up today. Thank you very much.